first debunk article you can find and instantly believe whatever it says. I mean,
do you think that's what I did?
No, I'm not saying that's what you did. I'm saying this in general to anyone. Like, what typically happens with the debunk articles is they like misrepresent the evidence, they omit details and stuff like that. So I would always encourage people, because what I do all the time, for example, if I want to debunk mainstream astronomy, I don't go look for another flat earther or someone that's skeptical or a geocentrist or electrical universe proponent and read what they have to say about it. I go read their papers and I go read their claimed evidence, what they claim it shows, so I can fully understand the strongest argument they have, why they claim the evidence shows what it does, right? And then I start to research it critically. If you don't like, if you're not able to still man the one side, then like you're just kind of being biased.
Yeah, it's a tough position to be in. Like if you want to debunk the mainstream, you've got a binary choice of, do you find supporting papers from the mainstream or supporting papers, or what you think is supporting papers from the fringe. All right. The mainstream is obviously not going to support your overall conclusion. And then you run the risk of someone just going, no, you're quoting a quack if you quote someone from the
Yeah,
fringe, right?
of course, it's super
That's
lame
difficult.
because. But what's funny though is like if you look at the current paradigm, all of the like popularly held positions in the current paradigm were considered fringe at first. So that's the great irony, right? Like when Einstein first proposed this idea, merely because of the fact he was throwing out ether alone, like the current understanding of ether, he was just completely ignored. Like he wasn't taken seriously at all at first. And of course, we all know that's like the mainstream will say it's the most tested and validated theory of all time. And it's like the framework of physics that's adopted by the mainstream. But he was fringe at the time. So you can look at the same as Galileo. Galileo was supposedly imprisoned, right? Because he was a dissident in terms of the idea that the earth was moving, and they called it heresy. If you look further into that total joke, his punishment was to live in like a huge castle, and it's like seems like that story's sketchy, but as the story goes, right, Galileo was punished because he was fringe, and of course, the mainstream position is that the earth does in fact move around the sun, and that geocentrism is wrong. So you can see, like, even if you're a current proponent of the mainstream positions of these things, like adopting the approach of just like kind of hand wave dismissing anything that's quote unquote fringe or dissident or challenging the current consensus is just kind of self-refuting because the positions you hold right now were once that very thing almost every time. And the idea of throwing the ether out was literally considered insane and laughable because it had been so sufficiently demonstrated to be true. And it was like the framework for all of Maxwell's equations. It was the framework for all of Tesla's inventions. So the idea that was completely didn't exist and there was nothing, basically there was no medium, that there was light was waving through nothing was like insane, right? So no one took it serious. Same thing with Newtonian mechanics, like which is like classical mechanics. When Einstein came in proposing that like the Newtonian mechanics was wrong and Newtonian gravity was wrong, that was considered insane, not even given the time of day at first. Right. So yeah, I think it's kind of a goofy way to approach it. Like I think if we're being honest with the way a lot of people in these rooms, and I'll land my plane here, but a lot of people in these rooms approach these conversations. Those same people, if we were to time machine back to like the times of Einstein, if I was jumping in the room trying to sell them relativity and argue for it, they would all like just completely hand wave dismiss it, say, we know that Newtonian gravity is true. It's the most tested and verified theory. We use it to build things. We know it's true. Your idea is insane. We know it can't be true. We know there's an ether and we know there's Newtonian gravity, right? If we rewound all the way to the times of Galileo, those same people would have been like, well, you're insane. You think the earth is moving. We know the earth's not moving, blah, blah, blah. For
They
sure.
were convinced by good experiments, right?
Um, I don't know. I mean, I guess that's a debatable statement, right? I mean, I would say the people, the electrical field theory proponents, were convinced by good experiments. Yes, for sure. And of course, a lot of the Newtonian mechanics is verified in many real world tests and experiments, right? Classical mechanics. So yeah, and of course, the stationary Earth. I mean, bro, default position.
It's verified to not work for high energy particles like the photons.
What?
Again, it's verified to not work for particles that have very high energy like the photons.
Yeah, that's not my point though. My point though is that at the time, the idea was wrong. It was a dissident view. And people in this room, if we all time traveled together, would say they would appeal to the authorities at the time. They would appeal to the consensus. Oh, all the world physicists are wrong and you're right. And, right. The same stuff they always do.
Make some predictions, like flat Earth. Make some flat Earth predictions. that globers would agree are consequences of a model.
Okay, I always force people to start with the motion. In my opinion, gravity and motion are the prerequisite to even talk about like a globe. Because you got to have gravity and then motion, and it coalesces everything in spheres, and that's going to give you the even theoretical possibility of having this omnidirectional, you know, bending water and many other things. Obviously, the motion of the planets and blah blah blah. Like it's the prerequisite to the entire idea of a sphere.
Gravity, I do agree, but why do you need a sphere to be moving in order for it to be a sphere?
Yeah, maybe not, honestly, but I mean, most interpretations and claims are that like it spins and coalesces into a sphere over time.
I don't think that's an interpretation. It coalesces into a sphere because it collapses upon its own gravitational field. I mean, its weight under the gravitational field. What the spin does is that it flattens it out due to the centrifugal force, so it becomes oblate.
That is true. That is true. But so it is gravity that basically causes the sphere to coalesce, or for it to coalesce into a sphere. So yeah, you're correct. It's just that over time, as it's doing that and it's spinning, they're basically going to work hand in hand, forming the sphere. But I will yield to you. Technically, you are correct. Yes, like the planet becomes a sphere because gravity is causing it to coalesce over time, and then the rotation causes it to bulge out or whatever.
Yeah, boy.
Whatever. So, unfortunately, or like conveniently, I guess you could say, is if you start with gravity, it leads you to motion anyway, right? Because as soon as you start to examine relativity, you get into debunking that, and you get into why was it really proposed. And if relativity isn't true, it has implications like the Earth's not moving, because you have to deal with MMX at that point. Anyway, my point is though, I can give testable predictions from that framework for sure, right? Like I can get like my geocentric framework is with an ether is far superior to your model. It's not even close. It's a complete and total blowout. Not even close. Because like a basic example, this is the Earth's not moving. When we made our observations, like at the time of Hubble, and we saw that it looked like the Earth was in the center of the universe, we would say, yeah, of course, our prediction is that it's going to look like the Earth's in the center of the universe because it is. And so the other side had to say, oh, it looks like it's in the center of the universe because it's an illusion that makes it appear as though the Earth's in the center of the universe. And then the illusion is caused by the universe accelerating and expanding in all directions, like a raisin in a loaf of bread in the oven or an ant on a balloon. So then you have to.
If we get to Mars and Mars appears to be at the center of the universe the same way the Earth does, what does that mean?
Well, that isn't actually what the claim is, though.
What's the claim?
The claim would be like for you to know whether or not the Earth is truly the universe, you have to get far outside of our galaxy. So it's not like a visual thing. Like the idea of like if I stood on top of a mountain and I can only see so far, then I would have an equidistant limit to how far I could see in all directions, right? And that would basically create a circle. And then I would think I'm in the center of that circle or all that exists, because that's as far as I can see. So if I went to Mars, it'd be the same. If I went anywhere, you can only see so far in each direction. You'd always think you're in the middle. But no, it's like the background radiation is distributed like supposedly homogeneous across the whole universe. Then you have this redshift going out. That redshift is going to look the same from Mars and from Earth. You'd have to get outside the galaxy to see the differences in the
Your
redshift.
claim can't be Earth at the center. Your claim has to be either galaxy at the center or solar system at the center.
Solipsism? No, because the evidence that the Earth is in the center isn't the redshift, right? Like the evidence is the empirical measurements that show the Earth's not moving, and just the overall distribution of energy, and like the redshift also matches the Earth being in the center. Yeah, you couldn't isolate that evidence and say that it's only that the Earth's in the center. You'd have to say within your claims of distances and stuff that it's in the relative center, right? Sure, but that's not what I'm doing. That's not what I'm doing. I'm just giving an example of how my model is far superior to yours, right? We have a stationary Earth in the center of the universe, so we would expect for it to look like the Earth in the center of the universe, which it does. It's also galaxy rotational periodicity, and basically they execute like circular patterns once a year and stuff like this. That I mean, they should have no concern with the Earth or what a year is, right? And also, it's the CMB. It's the CMB. It's the anisotropic distribution of energy that basically intersects on the Earth. That actually is specific to the Earth.
When you talk about galaxies, what do you mean?
The things that look like what we call galaxies in the sky. I mean, the observations are undeniably real, right?
Okay.
So it's like a giant rotating thing. So this is ironically actually where I'm going. So then you're like, oh, it's just an illusion that we're in the center because the universe is accelerating and expanding. But so then you have to like, wait, well, okay, well, something would have to cause the universe to expand and accelerate, right? So then we need some type of force or energy that does that. So you need dark energy, not because we observed it or even know what it is. It has to be there for our get out of jail card that
It's a
it's an
placeholder,
illusion
yeah.
that we're in the center. All right, now, but so we can all agree very simply that if the Earth actually is in the center, we don't even need that. So right there off the jump, a stationary Earth, a geocentric universe, is more viable in terms of the composition of the universe. If you don't need dark energy, then that model is obviously much more viable than a model that needs dark energy. And then when you get into, well, okay, the MMX showed the Earth wasn't moving, which would obviously mean geocentric universe. Then you get into relativity, which is gravity. You need that type of gravity, right? Well, when you look into things like the Coma cluster, in 1933, for its book, you saw the Coma cluster had 1% of the mass that it needed, right, according to gravity, to keep the galaxies in that cluster or they would escape. So you need that much gravity or whatever. So now you had 99% missing mass. That's what we call dark matter now. And of course, over time, we've made more and more observations. Like in 1955, they looked at the galaxy rotational speeds, and then in 70s, Rubin verified the issues with the galaxy rotational speeds and needs dark matter. And now they claim something like 85 to 90% of the matter in our own solar system is dark matter, 83% of the matter in the entire universe is dark matter, and that 96% of the entire composition of the universe is dark matter and energy.
But how
So,
many of
and
your claims rely on the Earth being a globe? Like your axis of evil CMB argument requires the Earth to be a globe, so you can't hold both those positions.
no, it doesn't. If the Earth was flat, we would just so we could still take CMB measurements.
No, you can't look in all directions. How are you looking in every direction on a flat plane? You can't look down to see
Yeah,
the CMB.
yeah. You wouldn't look down. You would just take the parts
Right.
where you're interpreting as down. It would be towards the outsides, obviously, and it'd be within like a torus field. And that's still the CMB, the part that is called the axis of evil, isn't about like how it looks down. It's just that the anisotropic portion of it comes to the Earth, and this would still be the case on a flat Earth. And then specifically that there's a 23.4 degree tilt, and they attribute that to the Earth tilted. But in the CMB, that 23.4 degrees extends far beyond our solar system, which
But that tilt
disproves. Yeah,
is through
meaning
an
there's an
axis of a sphere.
that's the claim. The claim is that the Earth is a globe that's tilted at 23.4 degrees, but the CMB revealed that there is an anisotropic distribution that's at a 23.4 degree angle, but that angle goes way beyond the solar system. So if the cause of that 23.4 degrees was just the Earth tilted, it would only be observed locally. You wouldn't
But
see
if you're
that.
saying the CMB has a tilt, right, then it has an axis.
No, it's not that the total CMB has a tilt. It's that the specific distribution that's anisotropic, it has a 23.4 degree angle in which it comes to the Earth. If the Earth tilted was the reason we get that angle, you wouldn't observe it beyond the solar system because, of course, the solar system is moving through the galaxy, and the galaxy is moving through space. So the local tilt of Earth would only affect your observations in the solar system. But this 23.4 degree angle extended way beyond it. By the way, the official answer for your side is that the data was interpreted because there is no answer for that, obviously.
It
So
does seem like a
What,
very convenient coincidence.
what do you mean by the angle extends beyond the solar system?
yeah, like that. Okay, so in really simple terms, the mainstream model of the universe is that the energy is homogeneously distributed, so it's evenly distributed, right? And it's isotropic, so it has no preferred direction. But what they saw in the CMB, and again, very crude, simple terms, is that there was a little bumpy portion of it. So it wasn't homogeneous. There was like a little bumpy portion. And that bumpy portion was anisotropic. It had a preferred direction, and that direction intersected on the Earth. And that little bumpy section of energy it was at an angle relative to Earth, and it was a 23.4 degree angle. That little bumpy portion of energy is seen in the CMB extended far beyond our solar system. If the reason that we have a 23.4 degrees is just because the Earth is a ball that's tilted on that 23.4 degrees, you would only see that tilted angle locally on the solar system because the solar system is moving through the galaxy, right? So that tilt would only affect what you see like observationally in that local system. Again, though, the answer for your side was that it was misinterpreted, the data, and they claim it's like interpreted with a bias. If you've ever looked into the guy that did the original like interpretation, like the computational interpretation, dude, is it like full blown atheist, Copernican principle advocate? I don't know what bias they're talking about, but anyway, what they did was Handwave dismissed the results like 4 or 5 times in a row, and they just kept getting the same thing, right? So eventually, they just said that the data is fundamentally misinterpreted. All right, so I don't want to debate the CMB though. I want to make this point to you guys, see what you think. Okay, so obviously we don't need the dark matter, dark energy. The reason we don't need dark matter is we're not going to invoke gravity as the cause, right, of the motion we see in the sky. And so, like, say with the coma cluster, I could say, well, no, there's a strong magnetic field that's holding those galaxies together. And when I see the galaxy rotational speeds, well, that doesn't work with gravity. They need dark matter because they go way too fast, right? Well, no, it's just a magnetic field. So I don't need a certain, because magnetism isn't proportionate to mass, right? Like you can have the same amount of mass, and like I could have 2 quarters that are the same mass, but 1 quarter could be 1,000 times stronger magnetic field than the other quarter size piece of mass, right? But with gravity, both of those quarters have to have the same gravity. So obviously, it's way more flexible to explaining the motion in the sky because it's not limited to visible mass, it's not proportionate mass. By the way, it's not just better in that sense, which is objectively better. You don't need dark matter, don't need dark energy. That means 96% of the composition of the universe is more like we have a more viable explanation for. But it's even more than that. It's like I was talking to Professor Park. He's like, "Oh, well, it can't be a magnetic field because they would have to be so strong to move the galaxies as fast as we see it, right? And we would be able to tell if there were that strong of magnetic fields in that galaxy."
Rob Parks just posted in the chat.
Nice. He said because spectroscopy, basically, like the spectral lines would break in the presence of those strong magnetic fields. There would be breaks in the spectral lines, right? But there's a phenomena where you can have a really weak magnetic field in the presence of plasma, and you can get like immense speeds within that plasma, even though the field itself is very weak. So what's interesting is there are tests that they've gone into a lab and they've taken plasma and introduced magnetic fields, and they've replicated like every type of galaxy, including the arms, everything. That's got to be super interesting to anyone that's honest, bro.
Yeah. So,
what's up, man?
Which plasma gives off lights? Yes.
What's up?
Plasma emit lights, emit photons.
It emits it. I mean, sure, it interacts with it.
Yeah. So why don't we see this then?
Why don't we see
it into your model? Where is this plasma?
It's literally admitted to be there in your own model, right? So it's called the ISM. Do you know what that is?
ISM now, abbreviation for what?
It's called ISM. It stands for the interstellar medium, and there's also something called the IGM, which is the intergalactic medium. There's also the interplanetary medium for our own solar system, and it's basically like gases that are ionized, which is what plasma is, right? It's like it's a very tenuous medium spread throughout space.
Yeah, and plasma emits light, so we should see this plasma light all over the place.
We do see it. It's admitted even in your own paradigm. It's called the ISM.
Yes, but not enough.
Not enough?
And
what does that mean?
Didn't you
just made that up.
No, didn't you post the image of the Horsehead Nebula the other day?
Wait, time out. Don't try to run away. You
no,
just claimed it was not enough. You just made that up.
Quick question. What is the Horsehead Nebula? Is that plasma?
Oh wait, I don't know. What I want you to do is
no, it's not. It's called neutral gas and dust.
I want you to acknowledge that you just made that up.
Another problem for you is we know how magnetic field polarizes light. Okay, hang on. Hang on. I just see a few problems with your suggestion.
I have to talk to you if you're incapable of being intellectually honest.
I am.
Admit you just made that up. You said it's not enough. What does that mean? Not enough. You just made that up.
Where is your calculations? Where is the observation that there is enough? Where there is enough plasma to create this? Because most of the gas and dust we see are not plasma.
Okay, so you claimed it wasn't enough. So how much is needed? What? Not enough for what? What's your comparative standard here? Just to make
that's for you to come up with.
So then you can say it's not enough because you just made it up.
No, because what is observed is that most of the dust and gas, which I suppose you think is plasma, is not plasma. It's inert gas and dust.
No, it's ionized gases.
No, like the horse.
In your own model,
there's
ionization.
Yeah. Listen, like
look, I'm going to help you out. I'm going to really dunk on you. Let's fast forward here.
No, okay, yeah. An example like the Horsehead Nebula is cold, inert gas and dust and not plasma.
Okay, what are you using to determine the composition of this medium?
What do you think?
No, go ahead, say it.
Spectroscopy.
Okay, so we're going to use astronomical spectroscopy.
Yes. Okay.
And you think that's super reliable, right? To know what's there. We can for sure know what isn't there using spectroscopy, right?
Because some, like in a gas, they will only emit a specific wavelength. Yes.
So you're confident that we can rely on spectroscopy to know what is or isn't there then, right?
Yes.
Okay. Well, check this out, man. So there's something called superfluid. We were talking about this earlier. And it was previously thought that we only knew about the superfluidity of helium could exist, but we now have established, like we've successfully created superfluid hydrogen as well. Okay. With superfluid, there's such a lack of, it has no viscosity, right? Superfluid has no viscosity. And so when it comes to the light, it's so undisturbed that you're not going to get absorption and emission lines. So if you were to look through superfluid or even just slightly less tenuous modalities of the helium or hydrogen next to superfluid, you actually would not be able to see reliably detect it with spectroscopy, even on Earth in a lab, much less at immense distances. So there could be a ton of superfluid, which would make perfect sense because it has no viscosity. So the bodies in space could move right through it with no resistance, and you wouldn't be able to detect it. Did you know that?
Yeah. Like light can travel around superfluid objects. Yes.
No, I'm talking about traveling it around it. Like it can travel through it, and you still wouldn't be able to detect it with spectroscopy. So light could go right through the superfluid, and if you tried to use spectroscopy, you wouldn't detect it. That's pretty cool, right?
Cool story, bro.
Very cool story. You're just gonna just not respond now that you don't have an explanation. Like, what's going on? Anyway, what I don't get is why don't any Glovers admit that it's pretty wild that in a lab they use plasma and magnetic fields and they replicated the galaxies.
Do you have any evidence of your claim that a superfluid is invisible, basically?
Yeah, it's well, for one, it's very obvious because it has no viscosity. So if you understand how spectroscopy works, right, then I'm just going to yield to your interpretation of light for a second. You believe that there's a photon, right? And that the photon is going to interact with material or a medium. And then basically the friction, the displacement of that photon is going to create specific identifiable spectral lines. Specifically, it'll be absorbed and emitted within that medium. And the absorption and emission lines are specific to the material or the element in this case, and you're able to detect it. Now, how is that photon going to interact within superfluid?
I don't know.
Well, it's not really going to react much at all, right? There may be minimal displacement depending on the state of superfluid. It's basically like a spectrum, but it would be very minute and very difficult to see. It wouldn't be a visible spectrum. It's basically frictionless. So it's like a frictionless, transparent liquid.
It isn't friction about the electromagnetic force.
I know.
There's basically no electromagnetic interaction between the atoms. What does this have to do with photons?
That's not the only time there's friction. I get friction when I rub my feet on the ground. It's just the interaction of matter. It doesn't have to be electromagnetic.
That is an electromagnetic force. You just exposed that you're illiterate in physics on the most basic
You
level.
you laughed about it because you're using the super pedantic aspect that all molecules are held together, specifically electrostatically. You could say electromagnetically. Okay, cool, man. Wait, are you saying light's not electric and magnetic? What are the two constituent fields of light?
I know.
Yeah, there's an oscillating. What kind of field? Electric and magnetic field. Okay, and then of course, all material intrinsically has electromagnetic components, including hydrogen and helium, even in the superfluid states. So why would that not apply? Why would friction not apply? Now it's basically frictionless, like it's very close to having no viscosity, right? I don't know why you're trying to look for some weird deflection or something. Like it's very common sense. If there's not much friction or viscosity in the medium, it's not going to have as noticeable of an interaction with the light. And that interaction, specifically emission and absorption, right, is how we're able to identify certain elements or materials with spectroscopy.
But doesn't light propagate in a specific way in like a helium superfluid?
Yeah, it's basically not impeded.
No, it scatters. And by the way, do you think though there are different areas with more or less superfluids?
What?
Do you think the universe is filled of superfluids everywhere, or is it just in specific areas?
Okay, so first of all, I gotta correct you here. Why did you say that light scattered in superfluid and then just skip past it like it was a statement of fact when I challenged it? You just made that up again. Can we stop doing the whole just make stuff up and act like you know it's true confidently thing? Light doesn't scatter throughout superfluid.
That's it. Hang on a minute.
You just made
Stick
it
your
up.
finger into the ground. Make up stuff. Well, that's what you do all the time, isn't it?
Yeah. Don't.
Yes.
Yeah,
Okay.
make
So
sure
where
you
is this? So where
whatever
is
you
this?
do, avoid the fact
Where
that
is
you
this
just made it up.
helium? How much? Where is this superfluid? How much of it is it? Does it vary? Do you have more in one place than another, and so on and so forth?
I got you. Yeah, you should know me better than to think that you're gonna skate past it. So you're gonna have to show some intellectual honesty, right? So you acted like you were correcting me. You asked how light interacts with it. I said it passes right through it. You said that's not true. It scatters. That is incorrect. Okay. If there is scattering, it's very, very, very little. It's almost zero. Okay. Secondly, we don't fully understand the nature of superfluid, but in your paradigm, certainly, but just in general, like what's invoked to explain it is different quantum states. For example, they don't really describe it as like the space in between atoms or molecules. They're basically overlapping waves, right? That's how they describe it in terms of quantum effects. Superfluid is crazy, but the light doesn't really scatter. That's the point, right? It's super, 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 super weak scattering. And this is my whole point. Because of that, you're not going to get the same spectral lines. You're not going to be able to detect the absorption and emission lines. And here, I'll still man your side. The reason that you get like readings of spectroscopy through, like, say, hydrogen or helium or whatever medium in your paradigm, right? You have little atoms in there that are moving independently, right? So like jiggling around. And so they independently act as like a scatterer. Like each individual atom is scattering, right? But that's not how it works in a superfluid. They claim that the atoms are in like a quantum state. So they overlap and they fluctuate collectively, not independently.
Well, helium fluid can scatter light. And what about polarization?
Okay. You see what you did? It can. It can.
It does. Yeah. It does slightly so.
Yes. Oh,
another question is, what does
any at
does
all?
does
You claimed it scattered
polarize?
Dude, admit you didn't know. Just admit you didn't know.
I did know.
Oh, you knew
I just
that
had to double check, or I sort of remember, but I just had to double check myself.
Oh,
so what about
you
polarization?
Knew that it barely scattered. Wait, time out. You knew that it barely scattered.
Yeah. It doesn't matter. So
Stop interrupting me, dude. Dude, I know that you're freaking out because you have such a fragile ego. You can't be wrong about anything ever.
I'm not rambling long around.
No, you're just not going to get away with it. So you wouldn't have brought up scattering if you knew it was very, very little scattering. That makes my point stronger. Okay. You presented it as though it was a refutation of my position. It's okay just to say you were wrong, but what you should now do is concede that you wouldn't be able to detect it with spectroscopy reliably because of the lack of scattering, thus the lack of identifiable emission and absorption lines.
So helium, just superfluid, critical helium, scatters the light ever so slightly, hardly affects it at all. But still, it changes the absorption lines.
Dude, are you kidding me? There may be a little bit of scattering. And again, I just gave you this answer. The difference is, right, within your paradigm where you believe in atoms and subatomic particles, in a regular element that isn't a superfluid, right? It's just individual little atoms that have space in between them. And they act independently, meaning the light is scattered on each little atom independently. They act as independent little scatterers, basically, right? But in a superfluid, they're overlapping. There isn't like space between independent atoms. It's a quantum state. And basically like the waves all overlap and it fluctuates as a whole unit, like collectively. So whatever scattering there is, it isn't scattering all throughout the medium based on all the different atoms. It's would be the slightest bit of scattering ever based on the collective fluctuation of that superfluid medium, and it's barely any scattering. So you can get some absorption and emission readings, right? But it would be very hard to read, basically negligible. It wouldn't be easy to identify. And we're talking about in a controlled environment in the lab where there's nothing else there except for superfluid and you're right on top of it, right?
I
In
think
a finite system. But we're talking about looking way out in the sky as superfluid. You would never be able to tell it was there.
I think it's okay. Now I understand. Yeah, because my question was: is light passing through superfluid like that? It seems like you are saying that this can affect absorption lines from the light coming through it.
Well, they'd be super weak, yeah. So you get my point is that technically there could be a continuous medium in space if it was superfluid. And it could be hydrogen or helium, for example.
And
So it
all
could be
that
this,
mass would not have any effect at all.
well, that's a thing. It's like it has no viscosity. So like, let's just use the idea of a planet
But
for
it
a
still
second.
has mass, though.
It has no viscosity though. So like so we can't identify, it's not visible, which by the way, you guys, that your paradigm believes that 83% of the mass in the universe is invisible. So whatever point you're trying to make right now would refute your own model because you believe in tons of invisible matter.
I still want to go back. How does the light passing through like a helium superfluid, how does the superfluid affect absorption lines?
It's not that it affects absorption lines. Absorption and emission lines are a byproduct of light moving through a medium. The fact that it's superfluid means there's barely any scattering at all. So there really isn't detectable absorption and emission lines. You might have a little bit, right? But it's very hard to detect because the main way that we get reliable absorption and emission lines are all the individual little quote unquote atoms scattering the light. So we get immense amount of scattering in each element in all mediums that we know about. And so we're able to now detect because
scattering has nothing to do with absorption lines. What are you talking about?
What?
Scattering has nothing to do with absorption lines.
Are you serious?
Can you explain how scattering changes absorption lines? Please go ahead.
Okay. What is an absorption line?
You tell me. You're the one who's making this claim that scattering affects absorption lines. So just go ahead.
Oh my gosh, dude, okay. He's like, I don't know if this is bad faith or not, so whatever. I'll answer it. So in your paradigm, you have a photon, right? And its energy is absorbed by an atom, right? Right? Okay, in your paradigm, you have a medium.
Sorry, go ahead. I'm walking my dog.
Yeah, you have a photon going into this medium. Its energy is absorbed by an atom, right? And then it causes like a higher energy state, like a vibration, right? And then it's like a very specific identifiable vibration, basically. And you're able to identify that. And we call that an absorption line. Okay. And you have an emission where they claim that there's an atom that releases a photon as it goes to a lower energy state. So absorption, higher energy state, emission, lower energy state. Scattering is the photon interacting with the atom or the medium, right? And it changes directions. So it isn't specific to absorption or anything like that. But the way that the medium interacts with the light in general and scatters it is how you're getting these individual interactions with atoms and photons. I don't believe in either, but it doesn't matter. The phenomenon is real. And you get either absorption or emission, then you get higher energy states, low energy states, and then you're able to detect the specific, basically, vibrational signature of each element interacting with light. And it's how we know when that's that element that's there. That's what spectroscopy is. Spectroscopy is super reliable on a local scale, like on a really controlled environment. Because we got super sensitive machines now. We're able to detect that exact like vibrational pattern or energy state.
Vibrational pattern, what do you mean, frequency?
Well, sure. I mean, like the photon is absorbed, the energy is absorbed by an atom, right? And then let's say in your paradigm, it would say that it basically like creates a localized excitation or an electron. So this is really in real life, this is just registered as a vibration. So it vibrates into a higher energy state. This is how I understand it. If someone wants to come in and correct me with how spectroscopy works, I'm pretty sure this is how it works, though.
Yeah, it has to do with differences in energy states. Go from higher to lower, basically. And then you end up with the dark lines or the absorption lines.
Correct.
But scattering of light will not change this, unless you mean it like it's already been gone through like a spectroscopy kind of effect prior to getting to the detector. The scattering, just for me at least, it just means that light is traveling in different directions due to things that I encounter on my way.
What did you say?
Just so we understand each other. When I say scattering, it's like how light is sort of spread out if it encounters, let's say, gas or whatever. Is that what you mean by scattering as well?
Yeah, I mean, I can see why you would bring up absorption, right? Saying that it's not related because it's more related to emission. Is that what you're saying?
No, I'm trying to understand what you mean by scattering of light, if we mean the same thing.
I don't know. What? Well, I don't know what else it could mean. It's self-defined.
Yeah, okay. Well, English is not my first language, so sometimes it can be a bit difficult to.
Okay, so in really simple terms,
100%.
right? Okay, so like light interacts with the medium, and then like whether you think it's atoms or molecules or particles or whatever, and it changes its path. The path of light is changed based on interacting or colliding with like atoms or whatever, a medium, fluctuations in the medium, whatever. That's what I would say.
Why do you think the direction of light changes?
Sorry, go
Because
ahead.
of fluctuations in the medium, right? Like I don't believe in like little subatomic particles, but I believe in the phenomena. You have like vortices and like
Okay, so
localized
what do you think
excitations.
is happening?
You have
So what do you
localized.
think
I just explained. You have localized excitations within a medium, right? They basically manifest as little vortices. They have different spins and momentums, whatever. I don't want to go through the whole redefining. What I
yeah,
don't want to
you don't
redefine the
want because you
photon
have
and
to
the
use
electron.
our paradigm.
Dude, look how goofy you are. You get so excited like you got a gotcha and you don't. No, I don't want to because I don't want to stay up for 3 hours redefining every subatomic particle. That's why I don't want to. Because look how in the weeds we are. Because you are both desperately looking for a gotcha when I'm explaining how obviously a geocentric model dunks all over you guys. You want to avoid that part and see if you can get some weird gotcha. You're not going to get one though, because I can always just default back to the mainstream. And now I just am saying what you're saying. The fact you take your brain out and hand it to the priesthood of scientism doesn't mean you're smarter than me or something. Like, no, I don't believe in the subatomic particles. I think they're reification fallacies. I don't think the electron is a charge carrying particle of matter. I think that's goofy, right? Hence why you say you cannot find it when you look at it, it's not there anymore, and you just use probability equations and you call them localized excitation of electron field and blah blah blah. Yeah, because it's not a charge carrying particle of matter. That's stupid. The photon doesn't actually exist. It's just the intersection point of the oscillating electric field and magnetic field that is light. You have a localized excitation on that intersection. You count them and call it a photon. It's not a photon. There's no such thing. You have localized. I just explained. You have localized excitations within a medium, right? They basically manifest as little vortices. They have different spins and momentums, whatever. I don't want to go through the whole redefining. I don't want to
you don't
redefine the
want because you
photon
have
and
to
the
use
electron.
our paradigm.
Dude, look how goofy you are. You get so excited like you got a gotcha and you don't. No, I don't want to because I don't want to stay here for 3 hours redefining every subatomic particle. That's why I don't want to. Because look how in the weeds we are. Because you are both desperately looking for a gotcha when I'm explaining how obviously a geocentric model dunks all over you guys. You want to avoid that part and see if you can get some weird gotcha. You're not going to get one though, because I can always just default back to the mainstream. And now I just am saying what you're saying. The fact you take your brain out and hand it to the priesthood of scientism doesn't mean you're smarter than me or something. Like, no, I don't believe in the subatomic particles. I think they're reification fallacies. I don't think the electron is a charge carrying particle of matter. I think that's goofy, right? Hence why you say you cannot find it when you look at it, it's not there anymore, and you just use probability equations and you call them localized excitation of electron field and blah blah blah. Yeah, because it's not a charge carrying particle of matter. That's stupid. The photon doesn't actually exist. It's just the intersection point of the oscillating electric field and magnetic field that is light. You have a localized excitation on that intersection. You count them and call it a photon. It's not a photon. There's no such thing. Light isn't a wave, it's just waving because wave's not a noun, it's an action. So it's the medium, it's a perturbation of the ether. So you have an excited state of perturbation of the ether, what you call speed of light's a rate of induction. So I did just define them. I'm not going to go through the weeds with you in them though, nor am I going to redefine bosons and quarks and Just because I don't want to sit here and do that all day. Also, I'm not gonna sit here and pretend I have an answer for all of that. I don't have an answer for every single subatomic particle. Me and Piezo did sit down, me, Piezo, Alan, Shane, we sat down for a few hours and did basically present the alternative understanding with an etheric framework with basically every subatomic particle. I'm sure we have that written up somewhere if you want to read it, but for the purposes of this conversation, it doesn't matter. The medium, when the light interacts with the medium, it changes path. And that's because you got collisions within that medium of the little constituent parts of it. And if you believe they're little particles or atoms, that's certainly your prerogative. I would say they're just little localized excitations within that medium. They typically manifest as little vortices. And in quantum, what happens is they look at the little vortices, which basically have a torus field geometry. Some of them have a different spin than others. They have greater momentum than others. And so they quantify them based on their properties. That's what they do.
So is all this happening within the container, within the firmament container?
I think so, yeah. I think it all exists
So
within
you're
the
pretty
firmament.
much in agreement, then it's just the finer details you're trying to hash out, is it? That nobody
What's that
seems to know
All
much
there.
about.
Say again?
Yeah. Well, you must seem to be both in agreement with the Globers. It's just the finer detail you're trying to hash out, which nobody seems to know much about. It's just a lot of speculation.
Well, I think what I'm trying to do is show them that exactly. I would say this is all speculation and it can't be verified at all. And it's intrinsically limited to speculation. Whereas they like to believe that they can know this stuff for a fact. But I'm just pointing out.
Speculate with authority, though.
Well, I'm pointing out that all the evidence that they've compiled by making observations of the sky and comparing them to actual tests and experiments that we have done in the lab, it's not like it's completely fabricated. Like quantum mechanics is a real field of science where we do scientific experiments. It's probably the most precise science known to man. It just flooded with a lot of like pseudoscientific interpretations and models and reification files and stuff like that. Anyway, they take a bunch of the evidence we get on the quantum scale, they look at the sky, they see similar things, and they assume that that's what's happening in the sky, but it is just speculation. The reason this is
doesn't
coming
mean
up,
much to the people on the ground. There's a lot of talk. Doesn't really mean much to people who are just walking on the earth.
well, maybe it doesn't mean much
talk
to you.
about
so-
stuff, So, I mean, what investigation could you make to discover
lead
where
the
the firmament
conversation.
is? Hang on. What investigation could you make to discover where the firmament is and the
I don't even know where the
container?
firmament is.
Well, wouldn't that be a better, use of your time?
No, it'd be a way worse use of my time because I know I can't get to where the firmament is.
Yeah, but you use that to claim lots of things.
I don't use the firmament to, what am I using the firmament to claim?
Well, the superfluid, the fluid layers that would make the sun that you saw in Antarctica do what you say it does.
We were not talking about that at all. Did you just jump in here and just assume what we're talking about or what?
You're talking. I know. I'm saying that the firmament, that would contain this system in your paradigm, is what you use to explain the happenings of a 24-hour sun in Antarctica.
No, I don't. What? So no, you're
What
not.
does
The answer
explain
is
it
no. You're
then?
not going to come in and completely derail the conversation. See, I knew that's what you were about to do. Then explain it. Then no, we were in the middle of a conversation. You can just come in and then just say I agree with Globers, and then demand evidence of a firmament and tell me to answer the 24-hour sun question. How does that work?
Well, the stuff you're talking about is in space and stuff that you've read about, and you kind of come to conclusions because you found some anomalies or some gaps in it that you can attack people about. But if this is happening as you say it is, it's happening within the container too. So you're kind of in agreement, apart from the. Well, I just think that
we're in patent disagreement.
Trying to find this container, this firmament.
We're in complete disagreement. We're in complete. The whole context of the conversation is we're in complete disagreement. They think the Earth is flying through an infinite vacuum. I said the Earth is stationary, which means it's a geocentric universe.
I was kind of more interested in the stuff we're doing on the ground. stuff
Oh,
like you
okay,
attempted to do.
okay, well, believe it or not, this room doesn't work where people just pop in and say, "Well, I'm more interested in this, so stop what you're doing because I own
Well,
you, and
I
now
don't
dance
take much
around
in.
like a little monkey and do what I say." I'm pretty sure you don't pay me. You want to pay my rates? My interruption, demand me to answer your random questions rate is $1,000 an hour. So I don't work for you, man. Why do the Glovers think I have to dance around like a monkey or something when they come in here? Anyway, bro, the conversation was somewhat interesting, which it was somewhat interesting, which is the point is, right? Like if we, because I don't want to just rant and maybe the room is tired of hearing me talk, but like to expedite the recap here, what we were talking about is like if the Earth's not moving, you don't need accelerative expansion of the universe, therefore you don't need dark energy. If you don't need to explain away Michelson-Morley with relativity, then you're not confined because of course just universe, Earth is stationary. That's what Michelson-Morley showed. If you just accept the results for what it is, like when we looked out the universe, it looked like the Earth was in the center. It's because the Earth is in the center. When we did Michelson-Morley, it showed that the Earth wasn't moving. It's because the Earth isn't moving. So now we don't need dark energy. We don't believe in relativity theory. So when we look out at the sky, we don't have to assume that gravity is causing all of it. So we don't have the issue of dark matter and how there's not enough mass anywhere. There's not enough matter anywhere to explain what we see, right? So they claim 83% of all the matter in the universe is dark matter. We don't have that problem. And you claim that there's tons of dark energy. So if you combine those two, that's over 96% of the composition of the universe in your paradigm is dark matter and dark energy. We don't have either of those problems with the geocentric universe. That means a geocentric universe model is 96% more viable when it comes to even just the basic composition of the universe. So then what happens is people are like, "Nuh-uh, how do you explain?" Da, 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 da. They never acknowledge the fact that what I said just an objective fact. But anyway, we were getting to the explain the da 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 da. All right. So it's like, okay, I was just going to tell you that galaxies are better explained within my paradigm. And you could have a super fluid medium all throughout space. And usually people say that's not true, or you'd be able to detect and observe it. That's not true. Using spectroscopy, you wouldn't be able to see the superfluid because it has no viscosity. So the light's not going to be greatly scattered throughout it, giving you the emission lines. You're not going to have absorption lines either because there's not a bunch of little atoms bouncing around in the superfluid absorbing the light, right? It overlaps within your own paradigm. It has quantum states that overlap. It moves as one continuous fluid, one homogeneous fluid, like it's one thing instead of a bunch of little bouncing balls or whatever, even in your own paradigm. So you're not going to get absorption and emission lines that are identifiable. So barely even in the lab, you may get a little bit. So when you looked out in the sky far away, you're not going to see it. So you could have superfluid filling every square inch of the quote unquote universe in space, and you wouldn't be able to see it with spectroscopy. And then what you would have is further excitations of the ether that would give you things akin to a plasma, right? And even weak magnetic fields within plasma can cause incredible speeds. And this would explain the galaxy rotational speeds that your paradigm can't explain because I'm invoking magnetism within a plasma. So that can explain the galaxy rotational speeds, whereas your paradigm uses gravity and needs to fill it with a bunch of dark matter because there's not enough gravity to explain the galaxy rotational speeds or to explain the clusters of galaxies sticking together or to explain pretty much anything. Pretty much every observation we see in the sky doesn't work within your paradigm. So I guess I'm confused. How did we not just objectively win? I'm pretty sure we do. Pretty sure our model is just objectively superior.
Is the Earth, how close to the Earth is this superfluid? It's just outside this dome, or?
Well, I'm not going to actually make a distance claim, right? But if I'm going to speculate, I would say that it's just above the closest layer of the container.
So how does, let's say, a supernova, how would the pressure wave propagate through this superfluid helium?
Why? Why would a wave works perfect within a fluid medium?
A pressure wave, yes?
Yeah.
You can send a pressure wave through it. Okay. So let's say if a stars blow up, that pressure wave should propagate outwards from it.
Say again?
Then that pressure wave should propagate from a supernova going outwards through this super critical helium.
What about what's the actual observation that's made that you're wanting me to explain?
I said if you have a supernova and that star is within in supercritical helium, that star would produce a pressure wave in it. It's like an explosion. So then that pressure wave should sort of propagate through the medium.
Wait, time out. Don't they claim supernovas like involve a lot of plasma?
Well, stars are plasma. No surprise there.
Yeah, certainly no surprise in my perspective. Although I think stars could be sentient, but I don't think you're ready for all that. But so what's the point? Supernova, they have
Sentient,
lots of
I think I
plasma.
give up.
Okay, good. Yeah, you
So
should.
yeah,
You're
and
getting
what
yeah,
about
your model got
polarization?
dunked
Yeah,
on.
no, okay. But as light travels through supercritical fluids, the light is polarized. So if it was even everywhere, it should have the same polarization. But when you do measure that, it does not.
What?
Different.
Why? No, there's all kinds of other stuff in space as well.
Yeah, but if the light is traveling through a superfluid, it's polarized. Same with magnetic field. Magnetic field also polarize light. So we should see this, and it should match your model. But
Why
does
should we
it?
see it? What do you mean? We should see it.
Because magnetic field polarize light.
Hang on, can I interrupt for a second? My
Yeah, go
daughter
ahead.
has an announcement. She was going to say Dave Weiss is a scammer. Anyway, it doesn't matter.
Wow, bro. How old is your daughter, bro?
15.
Yikes, bro. So you brought up supernova, which admittedly has tons of plasma, which perfectly matches our model, and that's a problem. How? Yeah, I know this is a tough pill to swallow because you're starting to
No.
realize that our model is
Yeah, I would.
superior, but it's okay, bro.
Yeah, I suppose when a supernova goes off, if it's within a liquid medium like a supercritical fluid, it would sort of have
Why do you
some sort
keep
of
adding
effect on it.
stuff to the fluid? It's super critical. What does that even mean? He didn't say critical.
Okay, critical then. But anyway, shouldn't it have an effect on it, even though it's frictionless?
Shouldn't it have an effect on it? That's your question?
Yeah, wouldn't you have some sort of pressure waves traveling through the medium?
Superfluid has no viscosity, bro.
Yeah, that's my question. I don't know either. But
Well, I'm just saying, like, bro, you can't. It's
would
invisible. It's basically invisible, man. You're asking me, shouldn't we be able to see the waves and the invisible stuff? No. And you're not going to get waves because it has no viscosity anyway. Right? So just think about it. Think about if you have a pool full of superfluid. By the way, Newton proposed this idea too back in the day. He didn't know about superfluid, but he basically proposed a superfluid. He called it a fluid akin to liquid silver that has no viscosity as the medium that fills space, because he knew that for gravity to be real, you had to have a medium with mutual contact of all the bodies. But anyway, I digress. So you have the superfluid. Just imagine a pool. You got this superfluid. It has no viscosity. So if I throw a baseball in there, once the baseball hits the water or the superfluid, it doesn't slow down. It just keeps going like nothing was there. Superfluid is amazing. And it's a real thing. I mean, it's like obviously I actually observed in a lab. So if I am going to throw the baseball in there with regular water, it's going to hit the water and cause ripples, right? And then the ripples are going to wave out based on the baseball size, its mass, and the force and all that. But not with superfluid. So no, whatever this supernova is doing, I wouldn't expect to see giant pressure waves within superfluid because superfluid has no viscosity, bro.
But still, there are like sound travels through, and pressure wave do travel through superfluids.
It may travel through it, but you're asking if I could look up into space at it and see waves. No, like yeah, it travels through it, but it has no viscosity. So what's the cause of a wave in fluid? It's the viscosity.
Still, pressure waves travels through superfluids. So that if a supernova then went off, these pressure waves should propagate and affect, let's say, planets close to the star or something like that. And you should see that they being impacted by these pressure waves.
What? Can you address what I'm saying? Superfluid doesn't have viscosity. Like inertia.
Can you send sound through superfluids?
I would assume so.
And what is sound?
Oh, this is a good question. I don't know. Maybe you can't. Because sound is just a vibration of the medium itself.
It's pressure waves.
Well, it's the vibration of the medium, though. Like, you can't have sound without the medium, right?
Yeah, exactly. So if it's
Can you
filled
hear
with
sound in a vacuum?
superfluid and you have objects creating very strong pressure waves, which is sound, this should have an effect on the nearby things in space.
I think you could. I mean, we're just getting into opinion at this point, speculation, but definitely. I think
Well, I
it
just looked it
could.
up. It says, yes, you can send sound through a superfluid, and it's an area of active physics research. Superfluids are unique because they can support different types of sound, such as quote unquote first sound and second sound. Second sound is a phenomena where heat is conducted as a wave, a property not found in normal fluids. First sound is a standard compression wave similar to sound in a normal fluid. It's a density wave that can travel through the superfluid. The second sound is this is a temperature or entropy wave. It involves the oscillation between the superfluid component and the normal fluid component of the liquid, like the viscous part of helium-2. This is a unique property of superfluids that allows for a type of wave motion for heat itself.
Yeah. So superfluid, like the flow, it seems to have no resistance to flow, but it doesn't mean that it can't sort of perturbate a sort of pressure wave going through it. I wouldn't imagine so. I'm not sure though. Just trying to think about that.
I guess that makes sense, yeah.
Kind of sounds
Because
like
it's not a fluid medium, right? So
it's really good at transmitting things. Like it would be even more efficient. Like somebody could be 10 miles away and you could whisper to them through superfluid. Does that sound about right? Like it's a perfect transfer of energy.
No, because I mean you still got the inverse square law occurring. So yeah, like that the problem with the sound emission is like that it goes out 360 and that's why it weakens over the distance that it travels. I think anyway. I don't know. Superfluid. Crazy.
yeah, I actually don't know
I
about
want
this.
some.
Trying to think about this for a second. Because like you make a good point, right? Like resistance to flow is not the same as just like a perturbation. But what's interesting about superfluid is that it moves as like this continuous, like single entity, basically. Right. Which is why they claim it's like it's not like your typical material that has like little atoms basically with space between them, but that it's all overlapping and that it moves as like singular fluctuation. Like it's like a holistic fluctuation of the medium. I mean, also to be fair, right? Like superfluid is not well understood in general, right? Like we're just trying to figure it out in physics, but
Can't you create an air bubble underwater that collapses too from sound?
yes, sonoluminescence.
Yeah, and that's really dope. They actually use that to study stars because it gets up to the temperatures that they say like is equivalent to stars, and it looks exactly like them, ironically.
But there's no correlation. There's
They say it's the same heat and they're studying that. I haven't heard that one. That's awesome, Taylor. What was that? So they're actually using the sonoluminescence phenomenon to study stars?
Yeah,
Yeah,
oh yeah.
which
They
is
call it
like
star in a jar.
20,000 Kelvin. Yeah.
Well, not completely, because
Here we go.
the luminous does not
Dude,
give
you
up
just got
the same electromagnetic spectrum as stars do.
Can you prove
okay.
that? No. Can you prove it? Where do you get that from? I'm interested. Can you share
So
with me the
yeah,
the
well, I
spectrum?
can look it up, but I don't think it does it create like X-rays?
I think you just okay. Yeah, definitely.
So
Well,
wait, you
yes.
know it doesn't,
It
or you
creates
don't
visible
think it
light.
does? Why do
It
you keep
emits
doing this
visible
thing where you
light.
say something with a lot of illusory confidence, and then once pressed on, you're like, oh, I don't really have any idea.
But science will tell us.
Are you sure stars send out X-rays, and we're not getting like similar spectrographs to the sonoluminescent stars?
Oh, it's
Star
visible
in a
light
jar.
that it's emitting. It's not X-rays.
I mean, I think he's confusing the sun with like what it puts off. I'm not sure though. Like, can you please send me the spectrograph, Stefan, of each to where you made that claim? You know, like what gave you
So
the
would
idea
that,
to make that claim
Spectrograph of what?
of stars versus the star in a jar?
Dude,
Maybe I've never seen spectroscopy of star in a jar. There
And how
probably
would you
is some
know?
somewhere. Well, the you need like fusion to create.
Did you know that
it's
some
its
people
own
X-ray
actually
medium.
though.
put forth the idea that the star in the jar phenomena is getting so hot that fusion did occur? Like somebody was actually speculating that fusion was occurring because I think it reaches like 20,000 degrees Kelvin. Yeah,
Well,
so these are actually ideas put forth, and they're actually using it to study stars because they actually reach similar temperatures to stars. Did you know that?
I haven't looked it up yet. What is
say
what
no,
the
no, just say no, you
spectroscopy
didn't
is?
know that.
Yeah, that's what I'm saying. So I have to look it up, see if I
That's
can
pretty
find what kind of
interesting if someone's
spectroscopy
proposing.
there is.
That's pretty
Yeah.
wild if someone's proposing the idea that fusion may have occurred.
Yeah, the temperatures that some people think that fusion I don't know if, like, everybody hopped on board, but it's like the temperatures that it's occurring, people were speculating that fusion could occur in there. I don't know. I just read a bunch of
That's
papers
pretty
about it,
crazy.
came across that
Yeah.
on some papers. So,
You know what
Stefan,
else
I don't
is?
know, like, I just think that you should hold back on making claims like, "Oh, yeah, like, they don't have the same spectrograph," because like, I'm the type of person that I'm, like, super interested in, like, seeing it, and, like, you just I don't know, like, you just shouldn't put forth, like, claims, like, if you really don't know. You know what I mean?
As I
Be
said,
wary of that.
I highly, yeah. The question was, does it create like X-rays?
No, you said you don't think it does, and I was wondering where you got that idea.
Well, you actually jumped in and said, no, not exactly, because it doesn't do this. It doesn't have the same electromagnetic properties. So you said it as though you knew it definitively. And this is what you've done like 10 times now.
Dude, I don't know if it emits X-rays, but it definitely emits visible light. Why is the X-ray thing a big thing?
I'm not sure if stars are even emitting X-rays. Like, I think that it's like the sun. He might be getting confused with the sun,
Well, they
but
claim sun is a star, right?
yeah, exactly. That's confused. That
So
could be part of
they
it.
do claim stars emit X-rays from my understanding.
But can we receive those X-rays from like stars from other galaxies? I don't know. I don't know. I don't think that it would. Yeah, they say they're like millions of light years away, and invisible light can travel that far. I'm not sure if like the X-rays would or not. But Stefan's. I think he's gonna share something with me on it because he obviously knows more about it than I do.
Well,
You can
well,
just
I
go
gotta
with
tell you
them.
guys, dude, if you want to look at something else that's super interesting, I'm reading about these sound waves and superfluid, and it's crazy, bro. The second sound, if you look up second sound, it's crazy. So it says that first sound has like the typical speed, or has 238 meters per second, first sound speed, and then second sound is 20 meters per second, and I guess that could be miles. It's temperature dependent. Because like one thing that's crazy about superfluid is it's like uh, convection is like insane. It's like incredibly efficient at heat transfer, like insanely efficient, to where they've had to like basically come up with some new quantum phenomena, like new quantum state of like super efficient heat transfer and convection. So apparently, sound inside the superfluid interacts. Its speed is relative to the temperature. Mm. Dude, superfluid is wild, bro. I'm just saying, if superfluid is what's filling all of quote unquote space, then that would explain why we're nowhere close to understanding what's going on there.
Did you say that we've created superfluid, like the experiment? I did kind of briefly try to look this up, but
Yeah,
do you know
yeah.
anything?
We've created superfluid with helium and recently hydrogen.
And they
what's
even
the
used it
process?
to detect the rotation of the Earth as it becomes an extreme accurate gyroscope.
Okay. I'd be kind of curious, how do they go about the process of like what do they pump the helium into a canister under a certain pressure and then introduce any sort of like electrical induction or
So
something?
No,
I
it's
don't
just
know.
lowering the temperature and
Yeah,
pressure. Yeah.
it's extremely low, like cryogenic temperatures. And so, like when you,
When it comes to some luminance, the spectrum is from ultraviolet to visible and potential, as I said, potentially and infrared. That's
So
the electromagnetic spectrum coming off
okay.
what's the word
But
sonoluminance.
called? What's the word called when you make it super cold with like liquid? It's like we did it in like science class, and you had to put your gloves on. It's like um, liqua back.
Liquid, you call it? We didn't we just call it like liquid helium? Or we didn't. We used
No, there's like
nitrogen. Yeah, we
liquefaction,
that's a earthquake thing, I think. I'm not sure I'm
In
familiar with the term though.
in high school, you'd only be dealing with liquid nitrogen. You're not going to be dealing with liquid helium.
yeah, of course, but that wasn't the point. What's the process? It doesn't. So anyway, that's all I know is that basically, I think it's really simple. Like you just take helium and then you just get it super cold, and then once it gets to those temperature, it they would say it like undergoes like some quantum transition or whatever, right? But it has zero viscosity, basically.
It's called the Bose-Einstein condensate.
I mean, it's kind of curious that when it
Yeah,
gets
that's good.
cold, it becomes more conductive or something of these pressure waves and whatnot. So it conducts them more when it gets colder. I guess maybe all the molecules are super close together or something. Like low energy state.
Oh yeah, see, okay. Um, Liquefaction is a process that can turn a solid or gas into a liquid, or create a non-liquid phase that behaves like a fluid. It is also something to do with earthquakes. So you're right. Liquefaction is the process where saturated soil temporarily loses its strength and behaves like a liquid. There you go. So
No, so
anyway, so
that's
that's
like
where
the
it
process.
does have to do with
Yeah.
superfluid, though.
Have you ever seen where they pump air up through sand and then all of this, like quicksand, basically? It's just
No.
that kind of. It's a similar. Yeah. They so if you take a chamber with a sort of a ground bed of sand, and then you start pumping up the air through the sand. Anything of any of like a more density than the sand will just it starts behaving like a liquid effectively.
Dude, guys, don't you think it's insane that they messed with plasma and magnetic fields in the lab and replicated the galaxies? Like, I didn't even know that. Like I was just thinking about like, okay, we see a lot of phenomena that's consistent with plasma. If you had like a really tenuous gas, then if it was ionized, then it would be a plasma, right? And what started me on that thought process is, for one, I realized that they did invoke plasma, and we know that plasma would give you like the medium needed for magnetic and electric fields and stuff like that. And clearly, whatever's happening in quote unquote space is electric and magnetic. But also, Tesla described the ether as the primary substance that has a tenuity beyond conception, meaning it's like rarefied. It's just insanely, mind blowingly, like inconceivably thin, right? And then I know that like with this like interstellar medium idea that they claim that there's like basically plasma, like ionized gas and different gases, but it's super, super, super thin, like thousands of times thinner than what the gases on Earth. So it just started me down this avenue where I'm like, okay, plasma, and then if you look at galaxies, they just look like magnetic fields in a ferrocell. Like they look just like a magnetic field. And magnetic fields have a vortex, right? So then you see like spiral galaxies, you see the galaxy rotational speed problem and all this stuff. And so you're like, okay, doesn't that just look like a giant magnetic field? Are we all going to sit here and pretend that that's not what that looks like? Like, really, bro? And if you had a giant magnetic field with a vortex, you would have things rotate around the center. And of course, they would claim that there's like gravity and everything's rotating around it. And then I realized they claim gravity wells, which is basically would just be the vortex, right? It would be a vortex. That's what the gravity well would be, basically. If things are rotating around that quote unquote gravity well, they conceptualize it like dropping a bowling ball in that fabric and it's going to roll around until it gets to the center. But if it's a vortex, it's just going to roll around the center. You're going to have that same geometry of a gravity well. You know what I mean? So it's like starts becoming very obvious that their interpretation of like relativity in space is basically just hijacking the ether, where they claim gravity is an emergent property, a secondary emergent property. Well, that's true. The effects attributed to gravity would just be an emergent property of the fluid background. And that it bending and waving and curving, well, yeah, that's true. That would just be the waves of a background medium. Space-time curvature would just be the waving. So yeah, it does technically bend, right? So it would be the waving of the medium. And then you would get the gravity wells, which would be like these vortices, and then you would get the rotational motion around the center of the vortices, which would be just the magnetic field itself. And then if you look at how they depict black holes, it looks identical to ferrocell images. Like the center of the magnetic field is like a little black hole. So clearly, we don't actually see black holes, of course, but they claim that there are certain areas where it looks like something like a black hole. It would just be our super strong magnetic field, which is basically an ether portal. So when you start to stack it all up, it's just so obvious that it's an electric universe. It's much more dense, much more local, it's much younger, it's much closer, etc. And everything's fluid-like. And you have the primary substance, the background medium, which is a fluid state that's super tenuous and rarefied. And then it's excited, it turns into different modalities, and then you would get stuff like superfluid as one of the initial states. So like the ether would basically be the primary state. It would be inertial, it would be stillness, be perfect rest. And then once it's knocked out of that state, you would start to get super tenuous mediums like liquid, super fluid, and helium and hydrogen and different states of that. And then you're going to get these gases. If they're ionized, you get plasma. So anyway, so you have like plasma and magnetic fields, right? And then what do you know? You look up plasma magnetic fields and galaxies, and you find out that going all the way back to the 50s, they were replicating galaxies with magnetic fields and plasma in a lab. and that even to now, like they're able to replicate like super precise like phenomena observed in the sky using different variations of magnetic fields and plasmas. Like, bro, really? Like, okay. It's
So
kind of like game over.
each galaxy must have its own magnetic field surrounding it then.